We've discussed dark matter many times on this channel, including some interesting facts, like how there's roughly 6 times more dark matter than regular or luminous or baryonic matter, and how nobody really knows what the dark matter is, or if it is. We've even discussed alternatives to the dark matter paradigm, alternatives that don't involve any form of particulate matter whatsoever. These go by different names, but one that we've talked about is the so-called modified Newtonian dynamics, or
I say name, you say
MOND. There have been several incarnations of it, and several past guests on the show, including Stefan Alexander, Sabine Hassenfelder, and others have looked at alternatives to the standard particulate WIMP-based dark matter paradigm. What you've probably gotten a sense from, if you've watched those videos, is why astronomers are so interested in dark matter. Or perhaps what's most fascinating is how astronomers figured out that it even exists in the first place. And now, it turns out, what we thought we knew about dark matter and how it helped shape the early universe may be wrong altogether. As you know, I'm an experimental physicist. I like doing experiments in the lab or at the observatory. But now I'm going to ask you to do a thought experiment. You could do it in your kitchen if you so choose. If you happen to have a toddler or a graduate student around, they may help you for free. Now, what would happen if you took a glass of water and poured it on the ground right in front of you? Don't pour it on your computer. Some experiments are best left to the mind alone. Obviously, the water spreads outwards. There's nowhere for it to really conglomerate and accrete. Water spreads out such that it minimizes the energy, the potential energy surface, which would be basically a flat plane of water molecules, 1 molecule thick, if such a thing could happen. Now, way back when, in our early universe's first few minutes, the universe was a roiling, boiling, bubbling brew of plasma, of ordinary matter. And if dark matter exists, there'd be some dark matter in there as well. It's getting dark. Now, what caused the luminous matter, or the baryonic matter, to accrete to form the structures that we use to trace the properties of the universe today? What caused it to conglomerate and accrete in specific locations, say here, but not here? Why didn't all those particles spread out uniformly throughout the universe? If that had happened, we wouldn't even be here to ask a question about the characteristics of the early universe. There'd be nowhere for matter to form. And that matter needed to form in order to form stars, individual stars, and then individual galaxies, and eventually clusters of galaxies. So water, or any other fluid, flows in a way that minimizes their potential energy surface. It would work the same way if water were poured out, so to speak, in space. It would just float away in a minimum energy surface, which would be a sphere, but a sphere of constant density. Now, astronomers make the simplification that you can actually trace the distribution of matter, luminous matter, the matter that we can see. We can't see dark matter after all, at least not yet, and maybe not ever if it doesn't exist. But astronomers can approximate galaxies as basically individual water molecules, if you like, in a fluid. And then the whole aggregate set of those galaxies taken together is like the glass of water to begin with. And you can ask a question. If there were galaxies, point particles in the simulation, in the early universe, uniformly distributed, something must have caused them to form giant clumps rather than just dispersing evenly over the flat cosmic floor. It's a huge mystery. Heading back to the kitchen, get yourself a muffin tray.
The Muffin Man?
The Muffin Man!
And take the glass of water and pour it onto the muffin tray. What will happen is most of the water will accumulate in the indentations in the muffin tray, the muffins themselves. I'm getting hungry just thinking about this.
Get in my belly!
There'll be a little bit on the interstices between the individual cups where the muffins will eventually form. In this analogy, the floor or the muffin tray is the background space-time. Where the space-time is uniform in a flat floor, you have no place for the matter to accumulate. With the muffin tray, there are lower energy surfaces, the cups in the indentations in the muffin tray itself, where the water will seek out a lower level. Where there's more matter, there's more gravity. Not just with muffin trays, but in the early universe as well. So if the early universe had some sort of indentation in its space-time curvature, then it would provide a place for ordinary baryonic or luminous matter to accumulate to then form stars, clusters of galaxies, etc. We've spoken in previous videos about how space-time can receive curvature on small scales, In fact, that's one of the many successes of the inflationary paradigm, though other models of cosmogenesis, like bouncing cosmological models, can do that as well. So cosmologists speak about curvature fluctuations, and where those curvature fluctuations come from is a matter of another mystery, but the fact that the curvature of space-time is tantamount to a gravitational force field is established in Einstein's equivalence principles. So once the curvature perturbations are established, there'll be a place for baryonic matter to form, and that will form where there was already dark matter accumulating earlier on in the universe's history. The paradigm is there's something that causes a fluctuation in curvature, which is tantamount to a increased or decreased gravitational potential, which causes dark matter to form and to cluster and clump in special regions of the universe as opposed to spreading out evenly. And then the gravity of the dark matter attracts the luminous baryonic matter that we can see. That's the paradigm of so-called cold dark matter cosmology that established and has established so long the paradigm that we look at and we study the early universe. But what if you found a massive object of ordinary matter in the middle of space that had no dark matter? That would be a huge challenge. The antagonist in today's mystery is the recent discovery of a galaxy without dark matter. Dun dun dun! A few years ago, astronomers, led by Yale's Peter Van Dokkum and others, discovered a galaxy with no dark matter. This dark matter-free galaxy goes by the very, very evocative name of NGC 1052-DF2. For the sake of just our conversation amongst friends, I'll just call it 1052 or 1052 for short. Through their measurements, they discovered that the gravity produced by this galaxy could be accounted for solely by its luminous matter content alone. That is, just the mere baryons that we see in this galaxy were sufficient to explain its gravitational properties. To put that into context, in the Milky Way, we astronomers believe that our galaxy is comprised of about 84% dark matter and about 16% ordinary or luminous matter. And most of that luminous matter is in the form of hydrogen and helium and the light elements on the periodic table, and just a tiny smidgen of which is the cosmic schmutz that makes us up. So to see a galaxy like 1052 with so little dark matter is a challenge to the cold dark matter paradigm. This galaxy is exceedingly faint. In the first images the team looked at from way back when in the year 2000, it wasn't much more than a blip in the background of galactic cosmic wallpaper that the team had looked at. Since then, thanks to images from a host of other observatories and even the Hubble Space Telescope, astronomers have finally been able to see it in enough detail to examine this galaxy's properties precisely. And what they saw in galaxy 1052 is quite astounding. They didn't only use the stars within the galaxy itself. They actually saw a swarm of small blobs orbiting around the blip, which was once observed in its entirety to be this galaxy 1052. Now these blobs have been known for quite some time, and they've played a big role in the history of cosmology, both in our galaxy and in other galaxies. They're called globular clusters. They're global, i.e. spherical, globe-shaped distributions of stars that are usually comprised of about 100,000 to maybe a few 100,000 individual stars. Living in such a globular cluster would be a nightmare because it would never get dark. You'd have stars surrounding you in all directions. These globular clusters in the early 1920s played a specific role in our understanding of the structure of the universe, providing evidence that the sun was not located at the exact center of the Milky Way galaxy. That's a topic I discuss in my video called The Great Debate. These cosmic fireflies swarming around a firefly hive are useful to astronomers because they can check how the gravity field of the individual galaxy is pulling on these orbiting, almost like satellites surrounding the larger host galaxy, in this case 1052. When astronomers looked at those globular clusters around 1052, what they saw was that the behavior, their orbital velocities and their properties of the globular clusters could be accounted for exactly by the mass produced by the luminous light-producing baryonic matter of 1052 alone. So it suggests that there's no dark matter, or it's certainly not a substantial amount of dark matter as there is in the Milky Way galaxy. This shouldn't be found in the so-called cold dark matter paradigm, or CDM paradigm. So it comes as a challenge, and it has to be rectified and addressed. This discovery could have some very far-reaching consequences if it holds up. Particulate dark matter that's comprised of WIMPs, weakly interacting massive particles, is not universally accepted, no pun intended. Some people say that there are unseen forces that cause the nucleation of galaxies to form, almost like a fine-tuning of galaxy formation. They provide the holes in the muffin tray without requiring dark matter to seed and cause the depth of the potential gravitational potential well. So our antagonist, 1052, stands as a challenge to the accretion model, wherein dark matter causes luminous matter to accrete onto it, because you have a galaxy that has almost no dark matter. So it should be impossible in that paradigm for this galaxy to exist. Or it could be something has stripped the galaxy of just its dark matter. So that would require some contrivances. We'd have to think of a mechanism through which the dark matter could get stripped away and completely rendered invisible to these astronomers' telescopes. Or it could indicate that galaxies can form on sort of the interstices between the muffin trays and depressions, and in a way that wasn't thought statistically likely beforehand. So, if dark matter is responsible for the formation of galaxies and clusters of galaxies, how did this galaxy get by without it? Of course, astronomers are incredibly creative, and there are many theories as to how this could occur, even in the CDM paradigm. Perhaps another galaxy stole a bunch of dark matter away from 1052, like a cosmic hamburglar stealing the muffin top buns. Or maybe this galaxy's current appearance is the result of a collision wherein a bunch of the ordinary matter in the galaxy got knocked away, forming sort of a mini-galaxy devoid of any dark matter. Now, both of these theories have plenty of challenges in order to address them, and it's not known if 1052 got knocked away from its dark matter halo, so to speak, from a big galactic collision. If it did, there should be some scars, some shrapnel left over from the collision of two more massive galaxies. Perhaps a tail, a streamer of stars tracing back to the scene of the collision. The only thing we know for sure is that if we can get a better look at 1052, we'll get a much better idea of what's going on. Similar to how the first early ground-based telescopic images of it really only just revealed it as a tiny blip of light. And then the Hubble Space Telescope and larger ground-based telescopes revealed it in more and more detail. How did a galaxy seemingly emerge into existence without any dark matter to seed it? With the Webb telescope, astronomers could track the individual orbits of stars within the dark matter-less galaxy, instead of just looking at the blobs, the globular clusters orbiting around it. Now, 1052 is hardly the only controversial, adversarial, antagonistic character in the dark matter dynamical story. In contradistinction to 1052, there's a galaxy called Dragonfly 44. It has a lot more dark matter in it than astronomers would have ever expected. Completely the opposite of 1052. As we discussed with Govert Schilling and his wonderful new book called The Elephant in the Universe, 100 Years of Studying Dark Matter, link in the video description, as time progresses, we'll get more and better data on galaxies like these two outliers. And that will help us refine and understand the role and even the existence of particulate dark matter. Cosmologists are hungry for more data, waiting for the next breakthrough from futuristic surveys, and certainly we'll learn a lot more about dark matter as soon as these data come in. Until then, I'll pass the time by eating a muffin. If you like this video, I created a playlist just for you, all about dark matter, including my interviews with Govert Schilling, Matti Milgram, and others. And if you'd like to watch a video about what astronomers already know about dark matter, from the only form of particulate dark matter that we know for sure exists, the neutrino, click on this video. And don't forget to subscribe.